So to start us off, let's see. I would like to introduce Professor Sophie Hallstedt, professor in the Department of Strategic Sustainable Development at Blekinge Institute of Technology, Sweden. No, actually Chalmers Technology, University of Technology. Yes, she recently moved. Yes, so from Sweden. So her talk will talk about strategic sustainable design, navigating resource constraints through systems thinking. Give us some kind of strategic setup. So Sophie, with that, please join me to welcome Professor Hallstedt.
Thank you very much for inviting me here. It is an honor to be part of this expert panelist and also opportunity to talk a little bit about my research to you. So my topic is strategic sustainable design, navigating resource constraints through systems thinking. And I will start with taking you through a resource funnel metaphor. So today, actually, companies today has quite good room of opportunities. But as you can see, that will actually change and decline with time. Maybe even you could say that the business, the opportunity of business or the different possibilities to make any changes are declining with time. And why is that? That is because we are in a sustainable society and the behavior is unsustainable. And for the companies, you can see that it will become tougher with legislation. So in Europe, for example, we have a Green Deal, which is a package of different regulations that will come. And already today, you can see that the sustainability reporting is much tougher, which also influence the design. We can also see that in 2035, there will be, for example, a requirement to not sell any new fossil fuel cars. On the market side, we can already see today that it will be more costly with different materials. It may be a shortage of different materials, some limitations, and also some components will be hard to purchase. So all of this makes it a bit more difficult for companies. So therefore, they need to navigate strategically towards sustainability. So what is needed here is to rethink, and rethink more radically than we are prepared to do today. So how can then design support a proactive and systematic approach towards sustainability? So I would say this is the short answer to this, and I have been studying this and done research on this in over 25 years, so this is my short answer. So the companies need to systematically integrate and implement a strategic sustainability perspective into the early phases of the innovation process, including a life cycle perspective. I call it sustainable product development. And I will go through it with you. So what I mean with systematically integrating and implementing is that the companies need to do this step by step. They cannot immediately make this change. So they need to start, if they haven't, they have to start now. And also a strategic sustainability perspective means that they need to have a long-term thinking and combine it with tactical approaches, but they have to be strategic. They have this long-term thinking and also need to include this in the early phases of the innovation process, because we know that about 80% of the decisions are taken in the early phases influence the sustainability profile of the product throughout the whole life cycle. So, what is then sustainability? Because if they are going to integrate a strategic sustainability perspective, it's important to understand what we mean with sustainability. So what do we then mean? Well, there are many definitions on sustainability. And why is that? Yes, because it depends what you want to make sustainable. We often recognize this Brundtland definition, I'm sure you know about that, meeting the needs of the present without compromising the ability of future generations to meet their own needs. So this is actually a core statement or a core value rather than a definition. So it's a core value to consider. Do we want to commit to sustain civilization or do we not want to do this? So this is actually something that we can choose to do or not. But if we want to commit to sustain civilization, then we can actually find science-based definition of how to reach a sustainable society. And that is what I have used in my research. And I will go through that also with you in a minute. But first I would like to show you this figure of the 3 dimensions of sustainability. And what is important here is to understand how these dimensions are connected. So as you can see here, they are as nested interdependencies. So the company, the economical dimension, is part of the social dimension. And the social dimension is part of the ecological dimension. That means that the business cannot become sustainable if not the social and ecological dimensions are sustainable. That also means that the company needs to understand how they can support the social and ecological dimensions to become sustainable, and how they can avoid contributing to that these dimensions become unsustainable. And research have taken this further, of course, and have looked into what are the mechanisms that can describe, you could say, the boundary conditions for these 2 different systems, the social and the ecological. And they have been looked into what actually are the mechanisms that can destroy these 2 systems. So if you understand what are the mechanisms that can destroy these systems, so we have the ecological systems with the functions that we need, and we have the social systems with these functions that we have and need. And then it has been identified that there are 3 mechanisms that can actually be destroyed, and there's 5 mechanisms that can be destroyed. And these have been translated to overarching sustainability principles. So overarching sustainability principles can guide you in how to reach a more sustainable solution. Or you could say guide you in solution moving towards sustainability. So in the ecological systems, it says that in the ecological sustainable society, nature is not subject to systematically increasing concentrations of substances extracted from Earth's crust. It means that if we take up a lot of fossil fuels and use it up, then we will have problems like we can see in the climate change. Another example, and the second one, is that nature is not subject to systematically increasing concentrations of substances produced by society. So that are components or substances that are non-degradable and that will actually increase in concentrations by time. We have examples of that too. Freons that were used in the 1970s and 1980s and destroyed some part of the ocean layer in the stratosphere. The third part is nature is not subject to systematically increase in degradation by physical means, meaning that if we continuously cut down the rainforest in Amazonas, for example, or we are overfishing in the Baltic Sea in a higher pace than the fishes are reproducing themselves, we will have a problem. And in the social sustainable society, it's described in a similar way. So saying that people are not subject to structural obstacles to health, influence, competence, impartiality, and meaning-making. So these are overarching principles that can be used. It doesn't say exactly how the solution would look like, but you can use them. They're very powerful to use together with backcasting. So you can use backcasting together with these principles to identify the ideal sustainable solution or the ideal sustainable vision that you will have for any context. And backcasting means that you put yourself with the mind in a future desired sustainable situation. And then you look back to today and then just ask yourself, what are the different choices you need to make in order to come to this sustainable desired situation? What are the different materials? What are the different manufacturing processes? What are the different steps that you really need to take to come to this more sustainable solution? So I mean that design can support a systematic and strategic approach based on backcasting from sustainability principles. The question is then, in which way can manufacturing companies design solutions for a sustainable society? That is very much dependent on where you are as a company, because it's about skills and knowledge. And you have to increase the skills and knowledge in this field, and of course exercises through support tools and methods that can guide and support the companies to integrate and implement these into routines and processes. So that you have it for a long time, and then enable these firms to coordinate these activities that also need to be on strategic, tactical, and operational level in the companies. So sustainability needs to be permeated through the organization in order to actually be successful on this. And then actually you can use this and accelerate the company towards sustainability transformation and make use of their assets at the same time. So I can show you some examples of some tools. We have developed some support tools in our research. We have about 20 different support tools. We have developed them with research projects together with companies on all these 3 different levels. So on a strategic level, we have, for example, developed a support tool that can be used to visualize and assess a company's current sustainability maturity level. So you know what are the different things you need to do in order to become more mature, so you can implement sustainability in product design. On tactical level, I've developed a sustainability design space approach. That is actually one of the papers I'm most proud of, because that was the most cited papers 2019, 1% most cited paper in the world, that 2019, that year. But actually that is as an approach that is helping the companies to identify the prioritized sustainability aspects, and is also combined with a qualitative measurement scale, how you could see what are the degree of the concepts, how it performs in relation to a sustainable solution. And on operational level, then you come to more detailed things. What are the materials that you're going to select? And in this case, we developed a tool together with Yuan Aerospace, and it was about material criticality. So this was actually a tool that can help in order to understand what are the materials criticality from availability and sustainability perspective in the early stages. And these are tools actually that have been applied, and those are also implemented at Yuan Aerospace, as we have been working with them in our research projects. I will also show you a bit of a more recent tool that I think is interesting, also developed together with Yuan Aerospace. But this tool is used to evaluate concepts from alternative sustainability scenarios. It is based on backcasting. It can guide the concept development towards sustainability in the early design phase. You can use it to compare different design concepts. And I see it as a complement to life cycle assessment that often focus on the current impact and how you can do less bad, so to say. So I think these 2 tools together could be quite interesting to use. So what is interesting with this is that we have identified some certain criteria aspect that should be optimized. So this company should try to optimize the concepts in relation to these criteria. So these are the key criteria, and then they are also developed 17 indicators that are connected to engineering characteristics, manufacturing, methods, materials, and geometric design. So what is interesting here is that you can compare then for different sustainability scenarios. So we have also quite recently done a study, an understanding of what is currently prioritized in 3 different aerospace companies. And then we see that they prioritize aspects like efficiency and safety. So if we today look into what are the concepts that actually could meet that kind of scenario and be appropriate from a sustainability perspective, then we can see that we have the gray concept that is doing best. If we move forward and look into the future, it looks like noise and circularity is becoming more important for the aerospace sector. And if we prioritize those criteria and the indicators and weight them a little bit more in this tool, then we can see that, again, the gray concept is doing best. But but is actually not as good as this. So it should maybe be interesting to actually develop a new concept that can meet these kind of criteria. And so on. So in the third scenario, as you can see here, that is due to this Green Deal package that I talk about in Europe, that also push a lot towards circular economy. Then if we weigh those criteria and indicators, we can see then that the blue concept would be the best concept to priority. That actually is more adapted to circular economy than the other concepts. So I think this is a little bit different way of thinking and what we do today in industry. So I think it's important to increase an innovative thinking, and also that thinking should steer the design solution towards sustainability. I will finally look into what are some relevant focus areas within sustainable design, according to me, because I think it's important to be responsible for us in order to meet a resilient and more sustainable society. So one area is defined value of potential sustainable solutions. To find a value, I think is very important to get the companies to get incentive to make a change. So we need to be able to support them with clarifying the business benefits for different choices at different time perspectives. And also to, for example, be successful in finding circular solutions and circular economy. To actually be successful with that, you need to work together with the partners in the value chain. So also you need to find common solutions in the value chain for circular and sustainable solutions. And of course then also be aware of rebound effects, and try to avoid rebound effects, which means that it is unintended negative consequences somewhere else, often in the life cycle phase, often in the user phase. For example, if you make more energy efficient engines, then in the user phase, the users may use these engines more, and so on, and then there will be no positive impact as you were assuming. Another part is that the companies need to be able to analyze and measure sustainability performance early in the innovation process. That is a challenge because you don't have all the data and the details. So here I think we need to look into different approaches, both qualitative and quantitative assessments, and combine those. It is also very important to have systems that can allow transparency and traceability of sustainability data. And this is particularly interesting now when we talk about circular economy. So how can you actually be transparent and also trace the data from one partner to another? And here digitalization comes in as well. I think that is a key actually to support and implement a strategic sustainable design. Both because digitalization can support in anticipating and visualizing sustainability data, increase usability, and even support in tailor-make tools for specific contexts. So I will finalize with saying that strategic sustainable design is about navigating resource constraints through systems thinking. It is key, I think, to do design with different and new approaches. I think it's also important that we can support companies to be proactive and a systemic approach, and have a systemic approach. And I think we should include responsible digitalization. And all that together, I think, can be something that can accelerate a transition towards sustainability. Thank you. That was all from me.
Thank you. Thank you very much, Professor Hallstedt. So this talk lays a very strong strategic foundation to frame our subsequent conversation. And now our next speaker is Professor Yong, who is professor at Concordia Institute of Information Systems Engineering from Concordia University. So his talk will talk about how psychological and the methodological tools can help overcome some barriers to achieve better and sustainable design and manufacturing. So please join me to welcome Professor Zeng.
Good afternoon, everyone. So I will start with some personal stories. Okay. So many years ago, I came to Montreal as a new international student. A couple of weeks after that, on my birthday, and I arrived at my rental place very late from school. And the letter was waiting for me. The letter was from the city of Montreal. And I opened it. The only thing I could understand, except my name and my address, was a dollar sign followed by number 75. My heart warmed. And wow, I thought, I knew Canada was very kind, very, 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 very nice. I knew it was so kind. And they will give me a $75 birthday present. So I had a very good sleep that night. So early in the morning, I woke up and I asked my roommates, I said, what is this about? They laughed and they told me, I said, well, yes, it's a gift from the city. It's a $75 fine because I put out my garbage bag at the wrong time. So that was my first lesson of sustainability in Canada. So about 10 years later, fast forward, I adopted a dog. And then, like a very good, responsible citizen, every time we went out, and after him, I would pick up the things, the waste he left, and then I brought it home and put into the organic waste bin, put it there, to be sustainable. Right? A few weeks later, again, I received a letter from the city, which is a warning notice. They said, well, the contents in the bag is organic, but the plastic bag itself is not. So, okay, I said, okay, I want to be more responsible. So I went ahead, ordered some compostable bags, waste bags, and I used them, and I feel so proud. I said, okay, I'm going to do a very good job. A couple weeks later, I received another letter from the city. They said, well, now the bag is good, and it's compostable. However, unfortunately, our city facility cannot process them. So I realized, being environmentally friendly is not an easy job. It's very difficult. It's a lot of a burden. So that was the three conclusions I got from these two personal experience stories. Firstly, the environmental burdens and the regulatory pressure are often barriers for us to be sustainable. Secondly, complexity of changes needed in design manufacturing, that is another barrier. And thirdly, psychological and practical industry resistance. In that case, municipality resistance is another barrier. And this realization actually landed me, secured me research funding from the government, study how our public behavior will have an impact on policy design. So that comes to this talk, path forward, how we're going to move forward. So from burden to breakthrough. So no matter what we do in our life, if we want to do it good, we need to put an effort. If it's an easy job, we put a little effort. A hard job, we put lots of effort. If we are not able to put the effort, then we cannot do the job. So what are the determinants for the effort? Think about it, what will determine our effort, how much effort we can put? So because my background is civil engineering or mechanical engineering, I thought about stress. Right? So I think there is a relationship between our mental stress and our mental effort, which is like inverse the U-shaped curve. If our stress is very low, our effort will be very low. In this case, if we ask you to calculate what is 1 plus 1, very easy, low mental stress. So you don't need the effort to make it correct. And however, if the task is very difficult, like Barbara just said, if it's a sustainability, to do sustainable design manufacturing, which is very difficult. So mental stress will be very high. In that case, even if we want to do something good, we don't know how to start, we cannot put enough effort there. So that is the problem. Therefore, if we want to put good enough effort, we have to make sure our mental stress is in the middle. So what is the mental stress? Many of us are from mechanical engineering. From engineers, what is stress? In mechanical engineering or civil engineering, stress is force over area. Or in physics, our pressure is a force over area. But what's mental stress? So what is the force in our mental work? That is task workload. Then what is our area when we do a task workload? That is our mental capability. So I call mental capabilities as 3 parts. The first part is our attitude, our emotion toward the task. And that emotion has a very important critical role. If we don't like something, we can't do it. So that is from 0 to 1. If it's 0, no matter how easy the job is, our stress is infinite. So we can't do it. So the best case, if our stress effect is 1, then we can make good use of our skills and knowledge. So the second part is come from our mind, our rational process, our knowledge and our skills, our critical thinking, creative thinking, systems thinking, all those design thinking, all those thinking skills. So we put them together, now we have called the tasks. So T is a task workload. ask is our capability, our human capability, and S is our stress. So we call it a tasks framework. So that shows how are we going to react or act in terms when we are giving a task. So then let's look at an interpretation of a task. So what is a task workload? A task workload is called a task. What is a task? A task is to ask. So no matter what kind of problems we have, a task we have, if we are able to turn a task into a series of questions, I think then we are decompose the workload into smaller ones. Like in this building, we have lots of nodes there. We have column 1, 2, 3, 4. It's 4 columns. Each column we are going to take a partial load. So how are we going to do that? Like in our daily life, we ask a question. We ask many questions. Each question is a smaller task workload. As a result, our stress will become smaller. So that is the task. Task is to ask. How to ask a question. That is a skill. So do we have a methodology to ask good questions? This comes to systems thinking, design thinking. Now we have ChatGPT, many generative AI tools. What do? You ask a question, they give you an answer. You ask a good question, they give you a good answer. You ask a bad question, you get a bad answer. So therefore, it's very important what is a task. You have to ask the good question. So we developed a methodology called environment-based design to ask questions. So question-driven design methodology. And then our capability has 3 parts, as I said, ASK, affect, skills, and knowledge. So there's skills including question asking skill, understanding skill, all those skills. Stress is the effect of all those completing a task. Now let's put into the context of a sustainable product design. In this case, our task is, what are we supposed to do in sustainable design and manufacturing? So we need to ask questions. Ask important questions ask right questions, which means that we ask a question, a right type of question on the right object at the right time to the right resource. So we ask a good question. Then we need to have the capability to deal with each sustainability tasks. Like Yuan has given 16 sustainability goals. So what are the capability for each one of them? What kind of emotion should we have? What kind of skills do we need to have? What kind of knowledge do we need to have? So that comes to, all those things comes back to, because you're talking about our ASK, this our human behavior patterns. Then we look, so in order to do that, we come to look at who are the stakeholders in sustainability goals. We have shareholders, designers, user, government, all the stakeholders there. Each one of them has their own goal, tasks, have their own capability. Therefore, we need to find a way to help them to deal with that. And then, so in that case, their own ASK, we ask, is that enough, sufficient to deal with their tasks? So what are the required ASK for each task? So then there's a gap. So the gap is the barriers everybody has in order to overcome those sustainability goals. So we have identified the 4 kinds of barriers. Number 1 is the emotion barriers. Do we have motivation to do it? What are our attitudes? What is our belief? What are our values, feelings, or ethics? All those things belong to this category. The second one is a logical barrier. Do we have that rational thinking, that strategy to deal with this kind of goals? The third one is knowledge. Do we have the knowledge, technology, and the other tools to deal with that? And the last one is the resource. The resource, the environmental resource, materials, energy, everything we have becomes the resource. If there is insufficient, there's insufficiency in each one of them, then we have a barrier. So when we deal with all those things, we need to consider all of them. Then we are able to achieve our sustainability goals. So we developed a tool, after this generative AI, we use ChatGPT developed a tool to do this analysis of a human capability. If you give me a paragraph, you write me a paragraph, we're sitting there, we can tell you what kind of A you might have, what kind of S you might have, what kind of K you might have. For example, you give one sentence there, and then we get the analysis, different examples there. We use this one for hypertension in patients, not sustainability. In the same time, we also started to do experiments on human being, looking into our decision-making process, our emotion process. So that in this experiment, in this process, we have EEG, we have this skin conductance, we have heart rate and respiration. We also have eye tracking, behavior, like we get all the data together, then we can try to analyze what's happening in the participant's mind, what kind of knowledge they might have, so to reverse the person's ASK. Therefore, we are able to find out the barriers of this person in achieving their goals. So all those things, we have applied this, starting from sustainability. Now we apply this one to construction business, in Montreal, to trying to encourage collaboration between stakeholders in construction business. And we also applied it to aerospace pilot training with the CAE, and we put them into simulator, try to figure out what's going on in pilots when they are flights the aircraft under different scenarios. And this one is the project we started with for this waste management for sustainable city, public city, citizen behavior-based policy making. We also applied it to cancer research, to hypertension research, different areas. I think this kind of concludes what I have to say. Thank you.
Thank you, Professor Zeng, for highlighting the potential of cognitive and human behavior aspect and its potential to support our sustainable design and manufacturing research. Now, our next speaker is Professor Gaetano Cascini, who is the professor from Politecnico Milano in Italy. This talk will show us that nature, we draw inspiration from nature, can really offer some innovative solutions, but there's a catch at the end. Not all, well, I'll leave it to you. So please join me to welcome Professor Cascini.
Thank you, Fiona. Well, actually, also big thanks to all of you for attending this seminar, this panel, and also to Tyson for hosting us. So, yes, I would like to share, also in the shape of a personal journey, as Yong did, my, let me say, initial enthusiasm for getting inspiration from nature as a way to inspire conceptually new solutions, but also realizing that not necessarily what is nature inspired is also environmentally sustainable. So we should increase our awareness and probably also broaden the picture of how we look at things with the tools, for instance, that Sophie was mentioning, to have a more strategic perspective on it. And this will be, how I will structure the presentation. So, well, I'm confident that most of you already know that what do we mean with bio-inspired design, but just to remark of why it is worth studying nature from an engineering perspective. And I would make it very broad. At the end of the day, living organisms share the same challenges that we human beings have. They are solving similar problems than human beings. They need to access to energy, they need to access to water, they need to build structures, they are transforming materials, they have, well, I didn't put the picture here, sorry, they have to manage flows of liquids, flows of air, just to say. And actually, it's already 3.8 billion years that they are practicing solutions to deliver those general functions. So, it makes sense to look at how they do so. What are the principles to get inspiration? So this is the starting point. And I must say that we know very well, I mean, you, at least when you were at school, you were watching documentaries, you know that often nature, living organisms, outperform us. I mean, you cannot compare the weight that an ant can carry with what we do. Just to make one, and so many others. So, I mean, we can get inspiration, and I can show you, well, these are pictures of, you can somehow recognize at least some of them, of bio-inspired products like the Velcro or the a kingfisher-inspired train, Japanese train, or, I mean, many others. I will share a couple of examples from our laboratory activities. One is related to a concept for filtering small particles, for instance, microplastics. You know that microplastics are an issue. You probably know that a good percentage, there is some discussion on how much, but a good percentage, let's say between 15–20%, probably more, of microplastics are generated by the fabric care cycle. I mean, we have a lot of synthetic fibers in our clothes, and in each washing cycle, we release a good number of fibers in the drain pipes. And at the end of the day, this enters the sludge. The sludge is brought in agriculture for, let me say, fertilization, and eventually we eat them. This is just to make the loop very, very simple. So we were attracted by the, let me say, some highlights of how manta ray actually, they collect food in their, say, mouth. And taking inspiration from this, we try to understand what is the working principle of these small turbulences that makes the small particle to hide behind the ribs of this solution. And, well, it actually works. It is very low maturity level, but here you can see that there is an accumulation of particles, 0.1, 0.3 millimeters large behind those ribs. Fine, nice, very interesting. Another example, still related to water treatment. We know that mangroves are plants that, among the few ones that can grow up in salted water, even in the sea. So they have the ability to separate salt from water. Interesting. So we might borrow an idea of how to separate salt from water. For instance, for desalination of water for agricultural purposes in areas where fresh water are not so common. A former PhD student of ours actually developed a concept. Here you see the third generation of the prototype installed in a small island in Greece, so nice location also, where with some panels which are fully passive, there is no production of electricity. I mean, even though they look like photovoltaic panels, but actually they replicate some mechanism, mangrove inspired, and at the end of the day, these 80 units produce 200 liters of desalinated water, and also as a byproduct 2 kilograms of salt that, I mean, could be used. And actually it feeds a greenhouse for cultivation. So these are nice examples, right? And we can say, well, look, these seem to perform very well, and probably they also have some value in environmental perspective, because, I mean, I was talking about something that was quite catchy, right? Microplastics or desalination, passive, I mean, it works pretty well, right? Well, we have other examples, bio-inspired. I mean, I would have several. I will present only one, which is inspired by this. What is that? Is a calamari. Among the properties of some calamari is that they can, well, I should tell that more scientific name, but at least we understand where we are. Among the properties they have, they can change color. And I will make it simple, but the way they change color is based on a combination of layers in the skin. The upper layer having some nano, let me say, kind of cracks or that under pressure open, so they allow to see what is underneath, and this allows to change the perceived color. Now, we consider this concept in a project with a very mechanical engineering company producing clamps. Can you imagine something more, let me say, basic and simple than mechanical clamps? And actually one of the issues there was that they wanted to simplify the process of properly tightening clamps without having any special tools to measure the tightening torque. So we said, well, we can take inspiration from these nice animals and make something that it is visible. When it changed colors, it means that I tightened properly without any special tools, right? Of course, in order to have something visible in industrial level, we are not going into nano cracks, we are going to something larger scale, and we want to have something which is visible with the naked eyes. So we played a little bit also with the concept of metamaterials, so introducing some patterns of cut that allows to enlarge the visible, let me say, opening under deformation. We made them with a water jet, and eventually we have a nice working prototype of a clamp that even just with a deformation of 3-4%, you can actually see with your naked eyes that it is changing color. Nice. But then you start reflecting in these and in other cases. Well, this is definitely bio-inspired. I'm saving the use of a tool, but I'm actually introducing very energy-intensive manufacturing technologies to make it. And also the rubber coating there, okay, it can be recyclable, but actually I'm mixing two materials, and probably this is not so recyclable, and so forth. So we started saying, okay, but does it really bring us in the proper direction? And actually there are many very famous examples, way more famous than what we are doing, about solutions that are bio-inspired that definitely outperform technical solutions, traditional artifacts, but they are way let me say, really far from environmental sustainability. One of these is the famous shark-inspired swimsuit. It was even banned because it was unfair to swim with these kind of suits. But among the others, well, these kind of materials are not so renewable. They are typically petroleum-based. There are some studies about, let me say, non-petroleum-based polymers to be used for replicating this kind of suits, but still not there. Non-biodegradable. The property provided by imitating at micro level the skin of the sharks gets worn, so it also has a short life. The production process is energy intensive. So multiple reasons to say, well, yes, you can save energy by swimming with this kind of suit, but you're not really using a sustainable product in environmental terms. And if you make a literature search, you will find a number of reasons so that there are good examples of bio-inspired solutions that have some serious environmental concerns. No, I don't want to go in details here, but here you find just a few, and if you make a search, you will find many more. So this is a point for reflection. So let's make a step back and let's think. How do technical artifacts made by a human being and natural solutions, do they differ? Well, there are substantial differences, and this is a well-known lesson that I would like to summarize in a few points. First of all, we human beings tend to reuse the same solutions everywhere on Earth, at all latitudes. I mean, how is it possible that substantially the solutions in Abu Dhabi, London, Moscow, and many other places are substantially the same with all local differences? The immediate consequence of this strategic decision is that we have goods and resources, materials, traveling all around the world, then consuming a lot of energy and having a huge impact. In nature, living organisms use only renewable resources available locally, and solutions change from the desert to the Antarctica. Second, for my colleagues from the manufacturing, I mean, they know very well because they are struggling to change this perspective. But typically our processes use a lot of heat, so high temperature, a lot of forces, a lot of pressure, and also often treatments that are, let me say, using toxic substances. In nature, the living organisms use only non-toxic substances in environmental conditions. I like this picture, or better, the concept behind the muscles. You know why? Because muscles do something that we human beings are not able to do, or at least we were not able to do until we started studying muscles seriously, which is creating adhesive bonds underwater in a shaky environment. We were definitely not able, they do. And this is something that we learned how to do. Something well known, our processes are typically, less and less fortunately, but are typically linear, which means that they produce waste. In nature, everything is circular, is working in closed loops. And something that really made me think when I read it first, we tend to use very rare elements to provide special properties to our products, to our technologies. Even that, for instance, the energy transition we are using now, or I mean the basics of our digital resources, the hardware systems, they use elements that are not so common. And if they are not so common, it means that there are some places on Earth that, let me say, suddenly they gain a strategic importance and they become reason for conflict. In nature, most of the solutions are made of carbonium, hydrogen, nitrogen, oxygen, and a little bit of phosphorus and sulfur, which are available everywhere. Interesting. So they outperform us, but they use a different chemistry. Now, I'm not so naive to say, so stop using everything from tomorrow. But in a longer term perspective, we can really reflect on how to radically change our strategies, our technologies. And so this is what I mean, borrowing from the basic message of the biomimicry people. It is a matter of combining not just the imitation, they say emulation of natural solutions or natural principles, but also the principle, the ethical principle behind, and therefore our solutions, our technologies should reconnect with nature. It is a matter of designing with nature, not just aligned to some concept existing in nature. So, I mean, there are so-called, to inspire the assessment of how good biologically inspired design solution is from the perspective of the environmental impact, there are so-called, for instance, life's principle, and everything is driven by a simple consideration. At the end of the day, in life, living organisms, the general purpose they have is just to create conditions conducive to life. So increasing life. This happens with everything, plants, animals, fungi, and everything. The only thing they're doing is they are just replicating more life. And probably we should adopt a similar basic concept also in our assessment. Are our solutions in favor of life or against life, in a broad sense, not just human being? And I mean, at the end of the day, this becomes a quite simple way of making our choices. So, well, very, very few takeaways. Bio-inspiration, I love it. And just to say that I really love, we opened a bio-inspired engineering track in Milano. So, I mean, I'm not against, you can imagine, but it is a tool. It is not self-sufficient. Sustainability is something that we have to really plan for on long-term perspective. So the lessons learned from, for instance, what Sophie presented is something that should really absorbed, assimilated to understand how to guide our reflections. A proper let me say, adoption of biological principles means to go, to start a journey. It's not a shortcut to do something very simple. I mean, you can. It will be probably also very nice and effective, not necessarily sustainable. And of course, this really requires also longer developing cycles. I mean, I'm not saying that this is really fast. It is not super competitive on a short term. So if we really want to undergo this kind of transition, it requires a kind of deal between, say, industry and research, and probably even the society at large, to have time to develop this kind of solutions, to fund research of this kind, and to allow to arrive to solutions that are really taking inspiration from nature. If I have 1 minute more, just a few words to present the Design Society, which is society, a scientific community interested in design. And why I'm presenting it, because if you like the topics that I presented, and I would say also the ones that were presented before and that will follow, here, you will find a community of people interested in discussing these topics. So it is a community, let me say, not of engineers, but generally speaking, people interested in design. We have members who are architects, designers, engineers, and not only, also psychologists, interested in design from the perspective of research, of education, and of course, practice. I will make it short, but roughly 700 members around the world, many different countries, many different seniority levels, and also really interested in the different perspectives of design. This is just a quick picture of our special interest groups. One of the leaders of the sustainable design SIG is Sophie. So just to say that we have very, let me say, qualified people who, who lead the discussion in these special interest groups. And there are very nice opportunities also for early career people. We have mentorship programs. We have, of course, others, publications, workshops, conferences, summer schools, if you are willing to participate in these kind of things. So, if you're curious, just type www.designsociety.org, or if you just want to ask us, me, Sophie, we are glad to provide all information you might want. Thank you.
Thank you, Professor Cascini. So the reason why Professor Cascini introduced Design Society is because he's the president of the Design Society, and I myself benefited a lot from interacting with this society, very welcoming, supportive researchers and members. So with Professor Cascini's talk, pointing out bio-inspiration is a great source of innovation, but not all of innovative solutions are inherently sustainable. So, and the talk pointed out some challenges related to manufacturing. So we're going to shift gear to move towards manufacturing-focused talks. To start us up, we'll have Professor Barbara Linke, who is the professor in the Department of Mechanical and Aerospace Engineering at the University of California, Davis. And then, floor is yours.
Thank you. Just need the clicker. Good afternoon. It is also my very big pleasure to be here. I want to talk about sustainable, smart, and human-centered manufacturing. And in my lab, that's called the Master Manufacturing and Sustainable Technologies Research Lab, we want to look at how a product performs, but basically coming from what process was used to make it. So we are interested in the physics of manufacturing processes, and especially surface finishing processes, but also polymer 3D printing, milling processes. But then we also need to characterize the part quality, mainly with the surface topography, but then near surface layer characterization as well. And I'll have an example how we use this for studies on bacteria attachment, but always with an eye to sustainability and intelligence, data-driven manufacturing or smart manufacturing. So we heard in the very first talk about the 3 dimensions of sustainability, but I want to also produce the picture here of our linear life cycle. So we want to have a product life cycle that is circular at some point, but nowadays we still have the linear view. But all those those life cycle phases are interconnected. So the decisions we're making for example, if we want a lightweight car, then we need to change the materials from steel to aluminum or other metals, which impacts the raw material extraction. Or if we want to have a product that's easy to repair, we need to choose different assembly practices in our manufacturing choices. So, for example, not welding or gluing everything together, but using threaded fasteners. And so there's many more dimensions to this product life cycle, decisions on the supply chain, transportation, where is our energy mix coming from. And then in the broader sense, we're interested in those up to 9 hours ultimately, we want to use fewer products and give them a longer use life, or maybe go back in circles with materials recycling mentioned here. And I want to point to something that we call leveraging manufacturing, where we can use manufacturing to our advantage to produce products with a better quality. So really thinking about a lever where we invest more resources in the production phase and get better use phase performance. So Professor David Dornfeld and his group has introduced this idea with an example of gear grinding, where you would, here's it's a little small, unfortunately, here's the energy demand and the percentage of surface roughness. So for producing a smaller surface roughness, you need significantly more energy. But this energy might be useful in the life of a product. For example, if this gear was used in a transmission for a car, then our low roughness would result in a low fuel consumption. So we outweigh the effects from our manufacturing process over the product use phase. And yeah, going back to manufacturing processes, so for example, our grinding process can be described with all the different physics, with forces, and we try to understand this process, but then also how this process impacts the surface quality of a part, and part quality as a larger theme, thinking about topography and near surface layer properties. And that impacts the part performance. So a very classical example for grinding processes is to produce bearings, where we're thinking about the friction behavior in its use phase, but then also me coming from the Sacramento Valley in California, producing a lot of food. We think about food processing surfaces, so corrosion resistant, hygienic behavior. And then you can also use fatigue as another performance factor. Unfortunately, often this knowledge, the data here in the form of a maybe digital thread, is not looped back, but we want to understand how the part performance and the process performance are related. And so here's some examples, staying with the food processing. I had a student who had an internship in an apple packaging house in Washington State and was looking into surface preparation for those food contact surfaces, often stainless steel. You can think about those big tanks welded together. And then those surfaces have different structures, and we were interested in how to characterize those surfaces to have a very low bacterial attachment. And so just with the comparison of an extruded surface versus a ground surface, the student was looking into bacterial attachment here for the extruded surface. You see bigger layers of biofilms. With the ground surface, you see those bacteria attached to the grooves and the ridges of our grinding grooves. But then also there was a correlation between the surface roughness and the bacterial count. So industry usually has some rough value they want to achieve, but they might not be able to specify how particularly the surface topography should look like and how this is achieved with the manufacturing process. Another example here, something we're just starting to study, how we can change the surface structure on lifting surfaces for helicopters, drones, aircrafts, to change the boundary layer flow. So by introducing some microstructure on an air wing, we can change the boundary layer. And so later then hopefully changing fuel use for the aircraft. And another example now with additive manufacturing, with 3D printing, with the wire extrusion process, where different layer heights and then with little sample pieces pulled over a surface showed different friction forces, and you could find a break-even point between the manufacturing energy and then the friction energy in the use phase, which we demonstrated by just pulling the sample. Another study where I have 2 more slides coming up is where we changed the build orientation, so from the 0 horizontal build to a 90-degree build, and different extrusion temperatures, so nozzle temperature here, would also change the wear behavior. So in this case, we used an automated friction tester. Those test samples were pulled back and forth for 3 hours, covering a distance of 2 kilometers. Here you see those some examples for those test surfaces, and the wear behavior was different for the different parameter combinations of nozzle temperature and printing direction. So this is not necessarily a design decision, but a manufacturing decision. How do you make a part that looks like what the designer thought about? And if you can, in this case here, study friction forces. So this here is the test setup with a force sensor there, going back and forth and looking at the forces in tangential direction. You could estimate how much energy is used, and this energy can then be used to build a life cycle model. So the energy to produce the raw material, plus the energy to produce one of those samples, plus those friction energies together into a model would give you, unfortunately this year doesn't show so well, but it gives you different break-even points for different parameter combinations when you would choose one solution over the other. And I want to also introduced the idea of process chains. So one process might impact the surface quality and the product performance, but then you also line up many processes in a chain for making a part. So for example, the 3D printed parts nowadays are often not of a good surface quality for the performance or for the function of the part. Here's an example where polyether ethylcotain PEEK plastic was used to print implants. So it has a bone-like structure. It can be 3D printed. But again, you would have the different decisions on print angles. But to achieve then a good surface roughness, which is below a average surface roughness of 2 microns, to have low bacterial attachment, you would need to do an abrasive machining process afterwards. And here you would see the different print directions have varying surface roughness afterwards. So really the interaction within a process chain is important. So while we try to understand how processes behave, we also want to make sure we educate practitioners how to use information that we're collecting. So one way is to use reusable unit process lifecycle inventories, UPLCIs. And in this case, only energy and waste are reported. So there are many more sustainability indicators like we had before, toxicity and other environmental impacts. But energy and waste are often the most practical ones and some quite easy to understand and to improve parameters. So these life cycle inventories have a prescribed way of presenting this information, and we have a series started in the Springer Production Engineering Journal where you see different processes mentioned. So you need the data, you need to present the data to practitioners and researchers. And one aspect of data would be the energy used, but even there you have to be careful where you draw your boundaries. So let's think about this here is just a turning process. There's a minimum energy to make a chip, to push the tool into the surface and shear off the material. So this is the basic theoretical process energy. But you need a machine tool to get the interaction between tool and surface, or tool and workpiece. And oftentimes the energy for the whole machine is much bigger than just the pure process energy. So process energy could be just 20 or 30% of the whole electricity you use for the machine. So where you draw your boundaries makes a difference. And then the machine might need other peripheral systems like tool changers, chip conveyors, and the machine stands in a factory. So, or even in a clean room where you have considerable energy as well. So drawing your boundaries is very important in any sustainability discussion. So for the grinding process, for example, there's a big scaling effect. So the grinding grid might be 10 times smaller than a cutting tool. So you have more friction going on. Your process energy is percentage-wise higher than a defined cutting tool process, but you also produce much better surface quality. So even though a lot of the conventional processes might have high energy, they are still not outsourced because they produce product quality that we need. So part of my studies is also around the machine tool energy. So with just changing the startup behavior of a spindle here for a grinding machine. So different startup times, you change the power profile. So the peak power might be important to what you pay as a company to your energy provider. So peak power and energy as the integral under the curve might also have a optimum point. And once you understand how each and every manufacturing process works with the machine, you can make bigger systems. So a seed grant that is quite interesting with Tec de Monterrey in Mexico is about figuring out how many 3D printers can you put on a truck together with solar panels, with converters and batteries to bring to disaster zones or rural areas. For example, here in Haiti, they printed umbilical cords or 3D printed parts for repair. So with knowledge about each system or each small unit, you can make a system that is useful to help society. Okay, and the last thing I wanted to mention, and we see here, going back to the EEG diagram here, or headset, we want to also capture the knowledge of humans. And humans work in factories, humans have a lot of decision power. Here with the example of a manual grinding process, we want to see how stressed humans are, what they decide to do with the tool, and how we can provide them more information for better decision making and for training. And so here's an example where we had 4 different subjects with different experience level in manual grinding in a motion tracking environment. And we were able to measure the force under the grinding or under the workpiece, and we were measuring the attention by looking at the eyes with those eye tracking glasses. And here you see different operators would have different attention, which can be correlated with the fixation duration. So somebody who is an expert would not need to look as long to a certain spot as somebody who has no experience. But then also here you see how people move the power tool. That also was something that we didn't expect in the beginning, but when we analyzed the different tool paths, we saw that the most experienced operator had a more complex tool path with these swirling motions, which only one other operator did. And on the right side, on a technical basis, you see here on the x-axis the material removal rate, so how much material is removed per second, and on the y-axis how much energy is spent to remove a cube millimeter of material. And some operators had a lot of data deviation, but the most experienced operator had the most consistent results and had the lowest specific grinding energy, which was also nice to see how we can utilize their way of doing things to give feedback and get to more sustainable solutions. So we would need to collect data. And here in the example, again, with a power tool, we can also collect noise data in addition to power and force, and then use machine learning to see the different states of the cutting operation and give feedback. But also the Dremel tool in this case here could be seen as a product, so we want to collect data from product use phase and give them back to the designer to make better decisions. But there's a lot of concerns about privacy issues, and people don't want to share their data necessarily. But yeah, we need to inform the designers to make better products. And so, yeah, I wanted to give a couple of examples to show how sustainability has multiple criteria across temporal and spatial dimensions, and how choosing your boundary makes a very big difference in your analysis results. And manufacturing can really help improve product quality, which I showed with a couple of examples. And then we shouldn't forget the human in the loop to bring back their expertise and help, or they can choose more sustainable strategies. And as always, work is not possible without the students, so thanks to them, and thank you for listening.
Thank you, Professor Linke. Give it to me. Okay, thank you. Well, thank you to Professor Linke, who actually pointed out there are many decision makings in manufacturing that we can leverage to improve the performance of the product, in turn trying to reduce the environmental impact of the products. Now, our next speaker is Professor Karl Haapala, who is a professor in the School of Mechanical, Industrial, and Manufacturing Engineering at Oregon State University. And his talk will point out some smart technologies that we can leverage again in manufacturing to enhance the sustainability. So please join me to welcome Professor Haapala.
Thank you, Dr. Zhao, and thank you everyone for being here and the opportunity to talk a bit more. So Dr. Linke set the stage well with some of the manufacturing work, and the other speakers have also talked about the systemic level thinking. And so here I'm trying to bring those together to look from the process level up to the system level. But before jumping into some specific examples that I have from work in our lab at Oregon State University, which is the Industrial Sustainability Lab, I wanted to come back to a little bit of context first. So one issue that has started to come more into play or more into thought over the last 10, 15 years is that we're actually working within these planetary limits, and so these have been set as what are the natural environment, or what's the carrying capacity or the capacities of our natural environment to support human activities that we've enjoyed over the past 10,000 years. And there's been some discussions that we've crossed over the tipping point on some of these. And so it becomes a challenge within engineering, especially if we think about making stuff, right? So manufacturing, designing and manufacturing, how do we not just minimize the impacts, but even create a benefit to nature and society, even through the production of goods, or finding alternative ways to meet societal needs that don't involve materials and goods. So that becomes a big challenge, and hopefully we can talk a little bit more about that. So this, my next slide here, kind of repeats some ideas that we've already heard, but I think this definition is really good when we think about sustainable engineering, sustainable manufacturing, sustainable development, and it captures the ideas that Sophie talked about from the Brundtland Commission report, and also this triple bottom line that we need to be thinking about. And so this definition is a couple of decades old at this point, but I think it's still very relevant for today. So we could think of it as the design of human and industrial systems to ensure that humankind's use of natural resources and cycles do not lead to diminished quality of life due either to losses in future economic opportunities or to adverse impacts on social conditions, human health, and the environment. So here's another definition of what we might think about in saying what is sustainable engineering. So some key components of this definition is that we need to be thinking about human systems and the industrial systems in a sort of symbiotic way. And also trying to avoid a myopic focus on cost or only on environmental impact or even one component of environmental impact. How do all of these things need to come together in developing solutions? And then we see, of course, on the right side, the need to have life cycle thinking in developing these approaches or developing solutions for society. So coming back to manufacturing, specifically manufacturing systems, now the integration of the processes like Barbara had talked about come together to form these systems, whether within a factory or a supply chain or entire enterprises. And as engineers, we're trying to improve or reduce costs, improve quality, productivity, sustainability itself, and also competitiveness. So new approaches are being developed all the time to do this. And so like Fiona mentioned, here we're talking about how can we leverage smart manufacturing capabilities to improve the sustainability of manufacturing. So smart manufacturing, or sometimes called Industry 4.0, encompasses quite a variety of different technologies that utilize data and information and try to break down the barriers within these systems, whether it's using augmented reality or simulation or artificial intelligence that we hear a lot about today. So a couple of years ago, myself and some others in the field looked at what has been suggested from a smart manufacturing perspective to that could be leveraged to improve sustainable manufacturing. So on the left side of the slide here is sort of a categorization of different smart manufacturing approaches, whether it's additive manufacturing or data-based methods, cybersecurity. So there's a whole range of technologies that are under development and implementation within industry. But then from an engineering perspective, how can we leverage those? So if we think of the design process, the design implementation process, each of these then can be applied in the design planning stage, as well as performance measurement, similar to some of the last slides that Barbara was showing, and then trying to make decisions on how to improve or intervene or even control our processes and systems. So moving forward, I want to touch on 3 primary examples that bring together, maybe these are a little bit focused on individual aspects of sustainability rather than how is everything being brought together, but that becomes a challenge. So first of all, I'll talk about a economic-based project, then social, and then environmental. So from an economic perspective, I want to cover some ideas of flexible manufacturing. So a lot has been talked about today, or in the news, of additive manufacturing and 3D printing. There's also more traditional flexible processes like machining, grinding, so that you can create a wide variety of geometries and customized parts for people that need them. So one of the processes we've been looking at in my lab is incremental sheet forming, which is a process that's been under study for several decades, but it's utilizing machine tools to deform sheets of material into custom shapes. So for this particular process that I'll describe a little bit more in a bit, we're applying a predictive manufacturing approach, or trying to start along that journey. So in a manufacturing system, we have a variety of machines and equipment that exist and are doing something. We can add sensors to those machines to try to gather information about them, which then goes into cloud storage, and then ultimately we can do something with that data and information to develop mathematical models, for instance, which then can come back and help us to control the process, maybe for improving quality, minimizing energy use, or just trying to develop inferences about the process. So this might be a little bit small, but this is a picture of an incremental sheet forming process. So we have a machine tool, kind of a little blow up here, a non-cutting tool, but a rounded tool that pushes down into the sheet metal to create a part, which is described graphically on the left side of the slide there. So if we look at this process, there's a number of parameters that we can control in the process setting. whether it's how fast the tool moves down or how fast it spins or what's the incremental step size. And then we also have product information. What is the geometry of the part that we're producing? So all of these factors come together then to define different quality characteristics or even metrics that we might use from a sustainability perspective. You can see on the right side there. So one of the projects that we were looking at was how could we use these parameters on the left side to understand and control the microstructure of the material that's being deformed. So the approach that we had taken, and I don't have details here in this slide, was to apply an AI-based method to map the process parameters to the actual microstructure that was developed, that then we could use to predict what could happen under different process settings. We ran into a few challenges in doing that, which I've kind of highlighted here. So there were some process level effects that reduced the quality of the material and made it a challenge to measure using the equipment we had. And so there's some microstructural analysis equipment issues that need to be addressed. And if we can take a step back and not look at the process or the material structure, maybe we can take information more directly from the machine to make other inferences. So, for instance, measuring energy use or dimensional conformance or direct measures of forces and strain. So those are some next steps for that work that we're contemplating. So next I wanted to talk a little bit on the social side. Again, kind of building on this flexible manufacturing idea is how can we take a more macroscopic view of all of the manufacturing capabilities that exist in an economy to be able to address either needs in an emergency situation or unique needs that might crop up that might otherwise not be able to be met by a typical supply chain. For instance, if you're needing to produce a low number of products or specialized products. So this work is actually funded by the US NIST through one of the Manufacturing USA Institutes, MXD. And so we're trying to say, how can we connect manufacturers with the capabilities that are needed to designers or specific needs that might need to be met. So the motivation for this project, of course, was the pandemic, and that's how it was funded. But the bigger idea is kind of shown graphically here, where we have people on the left side, whether it's, in this case, it could be a nurse at a hospital, for instance, in need of masks or other PPE that they can't get from their normal channels because the demands are so high. So is there some strategy we can use to match them with companies that have the capabilities or the equipment or the materials that that might be for other uses but would work in this case? So we've developed a software system that we're going to start testing with users over the next few months. And that system is kind of built on a microservice platform where we're developing these different microservices that are described here. So first of all, we have to do an item search to understand what is actually needed. And based on that search, what processes could potentially produce the part that is required, ultimately selecting the manufacturer, modeling the processes that manufacturer has to be able to quantify key performance indicators like cost. Maybe a customer is interested also in how much time or how much energy it takes to produce the product. And then ultimately supply chain optimization to be able to deliver that product to the customer based on their priorities. So here's a quick example of looking at a face piece for a elastomeric half mask respirator. So just kind of graphically showing here, the user could enter in a keyword, say they want a face piece. There might be information in the database, or maybe with enough data being collected over time, we could understand what materials are needed, what's a typical product shape for this particular product, what's the size. And these attributes here become important in doing our manufacturing process selection. So by understanding the materials, shapes, and sizes, we can define what are some potential processes that could be used to produce that particular part, assuming we can't buy it off the shelf. So in this case, maybe we could use injection molding or an additive manufacturing process. So now we can dig into our database of manufacturers and say, who's out there that could actually produce this type of a part using injection molding or additive manufacturing. So maybe we have manufacturer A and B. We have some information that these companies have volunteered into the database about what's their operations schedules, what's their capacities, capabilities, maybe what's their typical market. And then given that information, that can feed into unit manufacturing process models to be able to quantify metrics of interest, like how quickly can it be produced, how much will it cost, what's the energy use, for instance. So here's assuming some input information. These are some potential outputs that we might get. And then from these outputs, we can do an optimization to see where should this face piece come from. And there's the capability to optimize based on cost, time, energy, and then what we call overall best, but it might be a customized best depending on what their preferences are. So it could be a combination of cost, time, and energy if they have a different prioritization. And that will then tell us information about what manufacturers should produce, how much of what's the total cost, what's the lead time, and what's the energy consumption. And here we're using energy consumption as a proxy for other sustainability indicators of interest. So this is a little bit of a number chart, but the interesting thing is if you look at these different blocks, so this one is if it were the cheapest, fastest, lowest energy, or kind of a balanced optimization, what you see is manufacturer A and B, in some cases, actually both produce to meet the demand. So as expected, to get things the quickest, you'd have both produce something. But for the lowest energy, you actually wouldn't order any from manufacturer A, but order all of the parts from manufacturer B. So it's kind of intuitive. So to do this sort of a project, it's very challenging. The data is the big challenge here. Can you get companies to volunteer some of that information, like what's their operations schedules, what kind of equipment do they have, what kind of materials do they have, and how do you ensure privacy of that information? So there's still some practical challenges to make this sort of a system a reality. There are systems like this that do exist, but they typically require a lot of design knowledge from the person making a request, such as a computer-aided design file. So how do we generate some quantitative information from qualitative inputs that a non-expert might give? That's another challenge that needs to be addressed. And I'll wrap up here by talking about a third example, focusing on the environmental aspect. And so this is a project that's looking at the use of bio-based materials to reduce environmental impacts while also generating or creating a new economy or a bioeconomy. And so this work is part of a larger project to look at developing a bioeconomy in the US West. And so within my lab, we're thinking about what are the environmental impacts of that. So developing these new manufacturing or new manufacturing systems and processes around these bio-based products that may or may not be more sustainable or less environmentally impactful than conventional materials. And so how can we imagine a situation where we're able to collect the data in a more automated, maybe real-time way to make these decisions or make better decisions more rapidly about what should be done. So this is a detailed picture here that I can blow up a little bit, but this is sort of a big vision for this sort of a supply chain or a value chain, we might call it, for bio-based industry, but it could apply, the same idea could apply to any value chain, where we have sort of in the middle here, because that's my perspective, right? We have the manufacturing facility where there's information being generated about all of the processes and the activities that are being done. That then feeds back to decision makers within the system. And we could expand then to upstream materials development and end-of-life product management. So there's a lot of information that would be collected here that would inform decisions about what should be made. So at Oregon State, there's an effort through the Global Hemp Innovation Center to look at industrial hemp as a building block material for new products. And so it's a fairly simple material, but it has fiber and hurd that needs to be separated out into these two streams, but these can then be used as building blocks, like I said, for a wide variety of different products. So here, I'll quickly look at packaging, if I'm still okay on time. And so we looked at this as a potential opportunity as a new product to replace expanded polystyrene for a packaging material. So on the right side, we see a hemp-based mycelium, which is basically taking the waste hemp material and growing mushrooms on it into a shape. And so to look at that, we had to understand what are the parallel streams of manufacturing processes, and then for each of these processes, what are the different materials and energy inputs and outputs for each step. And then that information was fed into a life cycle assessment tool. We use SEMA-Pro, if any of you are familiar with that, and generated these results. So what's interesting is on the left side we see there's a high amount of environmental impact in the production phase for the expanded polystyrene. And across the board for the mycelium box inserts, it's much lower. What you will notice, though, is there's a slight increase in the use phase impacts for mycelium, and that's because it's a heavier material or a more dense material than the expanded polystyrene. So that was an interesting view there. So bottom line was we also found that the global warming potential of the mycelium or the natural material was less, which is sort of intuitive, but not always when you're using natural materials. And then we could see what is the source of the various impacts for the various stages. So most of the global warming potential, as also would be expected, is resulting from the heating processes. So to sort of wrap up here, I presented the big picture of this whole value chain with data being generated from all of these points through the process. So how do you ensure that people are going to do that, willing to do that, share the data, and also keep it, maintain confidentiality and data security. So these are practical challenges. Even for, if you think of farms, for instance, a lot of farms are not owned by the farmers but rented, so who's responsible for collecting that data and how does it get managed? Okay, as a final wrap up then is, I present a lot of challenges here, but the potential is that with these new technologies that are being developed, we can leverage them to improve the sustainability performance of our manufacturing systems. However, that requires a lot of engineering, system development to be able to do that. That's what I have. I'll acknowledge the US NIST and also USDA for the projects that I presented. Thanks.
Thank you very much. Thank you, Professor Haapala. So with Karl's talk on manufacturing, you start to realize, well, there are many considerations related to material. So our next speaker is Professor Chris Yuan, who is the Leonard Chase Jr. Professor in the Department of Mechanical and Aerospace Engineering at Case Western Reserve University. He will wrap up our panel discussion with a case study or focus, that is battery. So let's look at material perspective in battery. Can we recycle them? So the floor is yours. Thank you very much.
Thank you, Dr. Hello, everyone. Thanks for staying to the last presentation. I'm glad to be here to present our research on sustainable manufacturing of lithium-ion batteries for EVs. I will start with sustainable manufacturing, but we cover some research beyond manufacturing, like recycling of the batteries, and also the usage of the batteries on EVs. What's the performance? What should we pay attention to, etc. This presentation covers multiple years of research. We have done multiple projects in the past 5 to 6 years. Most of them published. So I'm going to show that one by one is a list. I will start with some sustainability issues of transportation at the EVs, and then manufacturing of batteries, and the usage of batteries. At the end, I have some information for recycling of lithium-ion batteries. So we'll drive cars, and we know that transportation really has significant issues in sustainability because the gasoline and the diesel cars burn gas, and the diesel, those are all converted into greenhouse gas emissions. At the transportation, in most countries, are the #1 category of greenhouse gas emissions. At many countries, like European countries and also US, set some strategic goals to reduce the greenhouse gas emissions from transportation sector. This is one of the goals US made to reduce the greenhouse gas emissions in 2026, based on like a 2025 gram per mile down to 143 gram per mile in 2025. How to do that? The main solution they sort of plan for is using EVs to replace those conventional vehicles because the EVs are cleaner, more environmental friendly, they generate low emissions during the operations. But EVs generate low emissions in the operations, but generate a lot of emissions during the manufacturing material stage and also end-of-life stage. So there are still significant issues associated with EVs in sustainability. We divided them into two categories. One is technological sustainability issues, like the battery technologies right now we use. They have limited capacity, so the driving range is limited. And also the batteries, when used for some time, the capacity will drop, and then we need to think about replacing the battery. It's a big cost to replace a battery pack. Besides the environmental sustainability issues for lithium-ion batteries in EVs, that includes the toxic chemicals being used in the battery and also being used to support manufacturing of the battery. Those toxic chemicals certainly will produce significant impacts on the environment. And also the manufacturing of batteries are energy intensive. And the usage of the batteries in EVs, although there's low tailpipe emissions, but there are indirect greenhouse gas emissions associated with the battery charging and discharging from the power plants. Right now, most of the half of the electricity in the US are generated by coal. In countries like China, there are even more. So this really depends on the fuel mix used to generate electricity. But certainly, there's still some amount being associated with the electricity used to drive cars. So the environmental sustainability actually is linked to technological sustainability because of the materials, manufacturing, etc. And when we address or try to address the sustainability issues of EVs and also the transportation sector, we need to look into the details of the lithium-ion batteries and say what's going on in there and what we can do to improve the sustainability performance of lithium-ion batteries, and eventually we can address the issues in the sustainability of the transportation sector. This is the manufacturing flow of lithium-ion battery pack, starting from the anode, cathode, and then following the manufacturing processes of like a mixing, coating, catenary, slating, etc. And then finally put together for a battery cell. And hundreds of, even thousands of battery cells are packed together into a battery pack, wired with the BMS system, battery management system, for controlling the charging and discharging, and then eventually loaded into the EV to power the vehicle. And during the manufacturing of the batteries, there are many factors governing the technical and also environmental performance of lithium-ion batteries. Here I just listed a few, starting from the materials down to the battery pack being produced. There are dozens of factors. They are playing roles to dictate and govern the technical and also environmental performance of lithium-ion batteries. Quite some toxic chemicals are being used in manufacturing of lithium-ion batteries. Some are contained into the batteries. Some are used to support the manufacturing process, like NMP. NMP is like a chemical solution, solvent used to support, to enable the manufacturing of battery electrodes. And also for lithium-ion batteries right now, they have to be assembled with the last step of the electrolyte filled in a dry room. So dry room means the whole room has to be dried to maintain the humidity level extremely low, like 0.5 ppm, something like that. So that will consume a lot of energy to maintain that super low humidity level in the whole room. And also, for manufacturing of a battery cell, there are more than 15 manufacturing processes being involved. Huge equipment, hundreds of feet long. And those equipment consume lots of amount of energy. Certainly that's a cost center and also generate large amount of greenhouse gas emissions. In order to address that issue, we have started a project to use water-based solvent, use water as a solvent, deionized water, to enable the battery manufacturing. So it's a water-based manufacturing of lithium-ion battery to replace the conventional NMP-based lithium-ion battery to make it more sustainable and cost-effective. So this is the manufacturing process of water-based manufacturing for lithium-ion batteries. It's similar, but there's some process being changed, like a drying process, vacuum process, etc. They're different from the conventional NMP-based manufacturing. And this is the materials used in manufacturing of the battery cells, the ratios between different materials in the battery cell, and then the coating is the same. And the drying temperature, etc., they are different. Timing is also different. Calendaring, the parameters is different. This is the components we designed into this is a virtual design. So we designed with software. We designed into a battery pack made by the water-based manufacturing process of lithium-ion batteries. This battery pack, the total weight is 417 kilogram, and then include these components and the active materials for the electrodes, the current collectors, etc. This is the comparison between water-based manufacturing versus conventional NMP-based manufacturing. The mass is the same, but the capacity is different. The materials are different, the solvent is different. This is the water-based, this is the conventional NMP-based. And then this is the material compositions for the water-based lithium-ion batteries. These are the components of each material. And we started the manufacturing energy consumed in the water-based manufacturing. We did the modeling for the water drying system, and then calculated and find out that the primary energy consumption could be reduced by 26.9%, roughly like 27%, if we use water-based manufacturing to replace conventional NMP-based manufacturing. So that's a significant savings of the energy and also the process greenhouse gas emissions associated with battery manufacturing. We also performed a life cycle assessment for this water-based manufacturing of lithium-ion batteries. This is the contribution analysis from cradle to gate of the battery cells produced by the water-based processes. So this is the components, and this is the life cycle stages. We evaluated with the recipe method, the global warming potential. This is the first one. We also compared the life cycle impacts of this water-based lithium-ion battery versus conventional NMP-based lithium-ion battery. So we found out that the water-based manufacturing is more environmentally friendly than conventional NMP-based manufacturing for lithium-ion batteries. So that global warming potential, this greenhouse gas emissions could be reduced by 27%. And this MEP could be reduced by even 88%. So that's a huge drop. And across all the impact categories, we can say that the impacts of the water-based process, the batteries, is lower than that of the conventional NMP-based batteries. So next, I will talk about the usage of the batteries. After we manufacture the batteries, they packed into a huge battery pack and then loaded into an EV to drive the vehicle. So for the EV driving, there are multiple factors governing the performance, the longevity, even the reliability of the batteries. These are some factors happening inside of the lithium-ion battery cells, depending on the driving conditions and the driving pattern and the driving behavior of the vehicle. So a lot of factors that could affect the performance of the battery and also the longevity of the capacity fading in the battery. But during the driving of the vehicle, the battery, we have to charge and discharge. So every time we charge the battery, we consume a certain amount of energy, electricity, that's being generated in the power plant and associated with a certain amount of greenhouse gas emissions. So in that way, there's still some indirect GHG, greenhouse gas emissions associated with the EV driving. And right now, if the capacity, there'll be an inevitable capacity drop for the batteries. It just depends on the driving condition, the behavior, the mileage, etc. But after a certain number of years, the capacity will drop to a level like 30%. This is the standard right now set up to replace a battery pack. If the capacity is dropped by 30% from its initial capacity, then it's recommended to replace the battery. And we have done significant modeling of work for batteries in EVs because it takes a long time and very expensive to do experimental testing of batteries in an EV. So we have done modeling. We developed these electrochemical models, multi-physics based, and then to model the battery degradation under different driving conditions in the United States with specific the driving mileage and also the ambient temperature. We studied the capacity fading for both the cycling capacity fading and also the calendering capacity fading. So no matter the battery is used to drive the vehicle, the car is just parked over there, there are always some capacity drop. It's slow, but there's still some capacity drop associated with that. We have considered both and then integrated them into our electrochemical model. And this is the predicted battery life from our modeling. We can predict based on the average driving conditions in each state of the US. We can predict the average lifetime of a battery pack. This is based on Nissan Leaf model. So it's roughly between like 6 to the longest is 13 years. So it depends on the driving mileage, driving pattern, driving frequency, ambient temperature, etc. And then we can quantify their capacity fading, and then until like 30%, then it's the time to replace the battery pack. And we studied the unit energy consumption of the battery for these 4 regions of the whole United States, interstate. So we divide them into this is for each state. We have the comparison between EV. This car is EV. This is the conventional vehicle. So the energy consumption, the EV consumes much less energy than conventional vehicle. We also studied based on the degradation of the battery, like after 5 years, the unit amount of energy consumption will be increased for the EV. After 10 years, it will be increased more. So we have both 5-year and 10-year increasing of the energy consumption on unit per mile driven. And also we consider the battery pack replacement. If the battery pack needs to be replaced, then that will be a huge jump of the energy consumption, which normalized into the unit mileage of that vehicle. And certainly, with the increase in energy consumption, the greenhouse gas emissions will also be increasing. So this is the increasing of the greenhouse gas emissions. This is for the battery replacement. And this blue line is for 5-year increasing. And this red line is for the 10-year increasing of the greenhouse gas emissions, the marginal increasing. And based on those data, the conditions, we have studied the adoptability of the EVs in the US across all the 50 states. So some states are really friendly to adopt EVs, but some states are not that good to have EVs. So we divide them into 4 categories based on 2 criteria. One is the lifetime of the battery pack. That's also an economic indicator. If we could use the battery pack for a long time, that means the unit driving cost will be much lower. The second is greenhouse gas emission reduction. If we replace a conventional vehicle by EV in that state, how much greenhouse gas emission could be reduced actually. So based on this criteria, we have divided all the 50 states in the US into 4 categories. Group 1, Group 2, Group 3, and Group 4. Group 1 are those states with the best performance for both longevity of the battery and also the maximum amount of the greenhouse gas emission reductions. This figure probably is hard to observe. Yeah, we have this map. So this map in different colors is like Group 1, Group 2, Group 3, Group 4. We have these states as the most recommended states for EV deployment, and then list. Oh. So, sorry, this is we need to go. Yeah, go forward. It's jumped. Yeah, so the red states, yeah, like Wyoming, West Virginia, those are the least recommended states because of the short battery life as well as the small amount of greenhouse gas emission that could be reduced. So that's the usage of the batteries. Next, I'll talk a little bit about recycling of batteries. We know that batteries were used for some time, we have to replace, but those replaced batteries will cause big problems for the environment if we don't recycle them. Right now, the recycling technologies for lithium-ion batteries are shredding, hydrometallurgical processes. Those are not profitable. They cannot make money, so that's why the recycling of lithium-ion batteries is slow. We have invented a direct recycling technology. This is based on real batteries retired from EVs. We can regenerate the performance of the battery materials. This is based on the cathode. We also have a lot of research going on for anode. So the performance of the materials could be regenerated other than recovered to be at the same level as the new materials. So we can recover the materials from the used batteries and then put them into the manufacture of new batteries, the same performance, but the cost will be dropped at least by 50%. That's the lab scale. In future, if for industrial scale, we estimate the cost could be dropped by like 80% over the pristine materials. That's a huge savings for battery manufacturers. This is some chemical testing results for the recycled batteries. Yeah, we have the paper just accepted in the environmental materials. It's available online right now, and also the university filed a patent for this technology. So the performance of this is the degraded materials without any treatment or recovery. And this blue line is the pristine, the new materials we bought from material suppliers. And this red line, this is the performance of the recycled materials over these degraded materials. So we could recover the performance from this line up to this red line. And it's very stable. This one only shows the data until 100 cycles, but we tested for 500 cycles. It's very stable, no problem. And we also did the life cycle impacts for this directly recycled batteries. We also did some modeling work. This is just life cycle impacts. For this comparison, using recycled materials will save environmental impacts. They are more environmental friendly because we can save the process on the materials manufacturing, mining, etc. So that's the main points of my presentation. The concluding remarks that EV is more cleaner, environment friendly than conventional vehicles, but there are still quite some challenges associated with lithium-ion batteries. A lot of research opportunities are there for lithium-ion batteries to be improved, to make it better, other than to fit the needs, to meet the market demand in future. So we still need a lot of research work by the community to be done together, other than to address this problem. Yeah. So, okay, so that's all.
Thank you, Professor Yuan. Now I would like to invite all the panelists to come to the stage. And so we can go from the side to have a seat. So I'm sure you have some burning questions. I have some questions I want to ask, but I would like to invite you who wants to ask questions, please line up. There are mics on the side that if you have a question, you can line up. Double check the sound. No, even no question. I'm going to jump start with my question. Oh, so the mic is over there. Would you?
There was a question, there was a number for a sustainability number. And I would like to know what is measured, what is measured and what does define that number.
There's a number? Which number?
Yeah, I don't remember the names. The lady
Was that the second one from the right?
Yeah.
Okay, that's for Sophie.
I assume you are thinking about the overarching sustainability principles, the 3 ecological and 5 social sustainability principles?
No, there were, in the environmental slides you had something like 84, 85, and it was sustainability number.
Yes, it was a way for us to calculate a sustainability value. So it was calculated in that tool that I described, based on the sustainability indicators. This value is not like a standardized way to measure to have a sustainability value, but it's in our tool we translated the sustainability profile with this value number. So this is one way to quantify sustainability.
So is there any formula that we can use?
You could say that the approach and the method to come up with that, it can be definitely used again, but it is context specific. So for each context you have to define the criteria and the indicators, but the whole idea, the whole approach is generic. Yeah.
Thank you.
Thank you. Thank you very much.
I have another question for
Sure.
you. Are these presentations available, or will you be sending to us?
So there is a recording. That's why we set up this stage this way, so that we can have a proper recording, that it will be available.
Not the recording, I'm talking about the
slides?
presentations, yeah.
Well,
The
it's up
slides.
to the panelists and see if they are willing to share. Maybe they have to remove some information. I'll certainly ask after this.
Thank you.
Yes. Next question, Larry?
Yes, I see a lot of good ideas about, many of these ideas I feel are trying to make industries more efficient, let's say. So aircraft industry, using less fuel, they become more efficient. Maybe they sell more airplanes that way. So all of these things are maybe dancing around the more major issues that, so this is kind of general question that I'd like at least somebody to address. Because I remember one of the presenter from Oregon was talking about how social issues are important, and his example was to find a way to make things more efficient when there's a disaster, right? But we should be avoiding the disaster in the first place. We shouldn't be making the oil industry more efficient. We should be getting rid of the oil industry. And maybe all this emphasis on electric cars is really great, but people should have less cars instead. So there's all this bigger issues around, and there's so much of sustainability research going into the aerospace industry because they're willing to fund it, but we should also have fewer airplanes and find better ways to travel around. So this is kind of big questions that it's hard for any one professor to answer, but I would hope somebody has some opinions on this too, and I don't even know who I should ask first. But
well, I can chime in first. So yeah, I don't think any of us in the room has the answer. If we did, then we could all go home. But but I think it's asking the question is the good starting point, and raising the issues is important. So I guess one of the challenges, and maybe that's back to the number that Sophie showed. So in her example, there wasn't one number even, right? So it depends on what is your perspective, and I think Yong said the same thing. What's your belief system and values, and a lot of that is also stimulated by what are maybe what policy or legislation, even from a company level, what internal policies drive some decisions. So I think understanding what are the key limits or something that we need to address is going to be important. So you mentioned air travel, for instance. So yeah, I think many of us flew here, right? So should we be flying? I think there's benefits to that we don't get from a virtual environment, but at the same time, there's probably a lot of travel that could be replaced with virtual technologies or new AI-based methods. So I think this is also the promise for more innovation globally, where we don't need to be tied to a particular place to develop solutions, but we can have people contributing from every corner of the globe to different solutions. So we don't need the physical togetherness, let's say, but maybe there's more democratization of tools and techniques and abilities. Anyway, that's my quick thoughts. I don't know if others have something to share.
I can add something here. I think it's about a system shift. So it's very complex and very complicated, because it's also about behavior and how we in the society are making our decisions. We have our needs and we want to live in a certain way, and we are used to a certain standard. And I think that also influences the choices and how the market is actually driving these different solutions that we see today. So I think in relation to, for example, flying, I think it will we maybe shouldn't take that for granted in future, that everyone should be able to fly these long distances and have this comfort. So I think it is a very tricky thing, and it's also very difficult, of course, to find new business models for the industry to survive. But I think in the relation to what I showed in the resource funnel metaphor, I think that this will be a shift if we are moving towards sustainability, if we actually think that this is something that we want to sustain, so to say, civilization. We need to make that shift happen, but it will be probably not so convenient.
Gaetano?
Yeah, actually, I wanted to say something similar, but Sophie explained much better, so I'm happy that she delivered the message. But I would like to add, yes, that we have, I mean, I share your doubts and concerns. And I would say here we have, I would say, two kinds of responsibilities. One is to reflect on how to make it viable at a higher level, at a higher system level, to convince companies to, let me say, to totally shift what they are offering. At the end of the day, what we need as a society is not to, let me say, to deliver more products, but what we need is to fulfill our needs. So, I mean, this sounds very utopic, but at the end of the day, one of the examples we were discussing this morning among us was you might want to reduce the, let me say, the resources consumption of an appliance, a household appliance, say a washing machine. But at the end of the day, if you are selling appliances, you have a limitation, because if you don't have the opportunity to sell more appliances, then you will fail as a business. If you shift to the perspective that what people want is clean clothes, then what you can do is to organize the entire business, providing people with tools to clean their clothes with a service perspective. And this is a way to make a transition in the interpretation of all the things, so that the life cycle of all products is extended, with the motivation to have things that last and consume less, because they still own to those who are in charge, responsible for the delivery of the service itself. At the same time, this can be also used to, let me say, by design, guide a proper use of the products, or generally speaking, of the artifacts. I mean, in the example of the, it was very interesting, but I mean, to read that the life of batteries also changes based on the driving style, the driving patterns, and so we should probably design the cars. Well, it would be better not to have private cars in a sense, following your reasoning, but still, if you have some shared cars, we would like to have cars that make me drive better, in the perspective of consume less, of having a longer life. So we have also this, and this is the second kind of responsibility, to have products that are a kind of incentives to a better use, where better means more sustainable. It is a challenge, by the way, and definitely, and here I'm closing, it means that we should make a kind of societal deal for longer term impact, because as far as we are competing on an everyday basis, it is very hard to make this paradigm shift. So it requires necessarily a deal at the societal level, by rules, by policies, by I mean, whatever, but it does require, and as global as possible, because if you do it in one single country, it won't work, of course.
Mm-hmm. Yong, maybe you have some comments on human behavior?
Sure, I'll try. I think your question is very insightful and reflective, because it comes back to the fundamental human needs. So we come to our core message today is sustainable design. So if we took keywords, one is design, another one is sustainability. So when we say design for what? Mm-hmm. So we design for human needs, because all the products, one way or another, is to fulfill human needs. So on the other hand, the design, the product will come back to change our needs. Like I just mentioned, right? We get electric car, we get airplanes. So because of those advanced design, our needs start to go up and up and up, so become more and more greedy. So that is these two interaction between the design and our needs. This is evolving altogether. This comes to a sustainability issue. In order to fulfill our needs, then it generates some unintended outcomes, consequences. So those consequences will come back to shadow our real needs. And then this comes to the necessity for sustainability. But when it goes up to a certain extent, it becomes unsustainable no matter how hard we try. So then comes back to your question. Should we get rid of a car? Or should we get rid of the oil and gas industry? Or should we get rid of those things? Because then this comes back to what kind of lifestyle should we take, right? So I think there's no single answer for that. This comes back to what it says, belief system. What do we believe? What kind of life we want to take? I think that this is an engineering program. This becomes more like the philosophical or even like a social issue. That's my, okay, thanks.
Great, thank you. I think there's another question. Please go ahead.
Thank you. My name is Eduardo Quiroga. I'm with the McGill Life Learning Center. I have an observation, which could be a question. I'm going to address it to Dr. Hallstedt. In one of your graphs, you had economics and business in the same box. They're not in the same box. Right now, we have two businessmen with degrees in business, literally destroying the world, meaning the economic system that we have been using for the last 40 years. And both have degrees in business. So what I'm saying here is that for a long time we've been saying business, economics, all same box. No, they're not in the same box. Not now, at least. In business, you're legitimately interested in making money. And those two businessmen, they're going to make a lot of money. But they don't care about the rest. In economics, you're taught not to worry so much about money making, but welfare. Everybody should be better off by whatever policy you're proposing. So I think in future policies, in future graphics, we should make a distinction between the economics and business schools, and maybe even consider adding courses or whatever in each discipline, so they're aware that you can go all the way into business and really destroy the world, as we're almost in the process. Thank you.
It's more of a comment, right?
Yes. Yes. Yeah, and the panelists also will probably support. I think, I mean, as I agree with you that it is more complicated than put business and economical dimension all together. I think this is a simplified way to say that the business and the economical system is part of the social system, and like the business cannot be sustainable if the other systems are not sustainable. But actually the power is very much in the business dimension and the economical dimension. So yeah, it's complicated. I don't know if you want to comment.
Yes, I think Yong has some comments.
I think this comes to, when it comes to business, comes to game design, right? What kind of game you want to design for the world? Like we are all part of it. So you design, okay, this is, you do this, you succeed, you do that, you are better off. So this game, if we are, in Western world, the game is designed kind of autonomous, it's evolving. So when we do sustainability, when UN is involved, they're trying to intervene in this gaming to add some constraints here. So what kind of new game mechanism or market mechanism can we have so that the business, sustainability, technology, and the humanity can all together? I think that is a very big issue. I don't think we have a good answer for that. Yeah.
Yeah, let me add a very philosophical kind of response. What is money? What is money? What is money? Yeah, what is money? I mean, I'd like to hear your opinion. What is money?
It's just a means of exchange for goods.
It's simple. A promise. It is a promise of a potential benefit.
Sure.
Right? I mean, it is not actually a change itself. Money is a promise that you might get some benefits in the future by using that resource.
It's a means, yeah.
If we really understand this meaning, then what you referred as welfare, or I mean, being better for the future, if we really understood these, they would connect again. Of course, this is, I understand it is a kind of a topic, but yes, I mean, the only difference is that we don't perceive at an individual level what is the issue of discarding the collective situation. That's the main point, because money is a benefit, I mean, it's a promise that you use at the individual level without really considering what are the consequences on the society, on the earth, on life on earth of being non-sustainable. So I mean, it is extremely challenging, but we should try to let me say, to reconnect these two meanings, because at the end, if you really dig, they are not that distant. This is my opinion.
But this issue comes up at the university. When we split up both levels, and in 2018, there was a review saying those MBAs were an issue because they were constantly moving money around. That was what they're trained for. Of course they were trained for. I'm not against it, but I'm just observing. Whereas the other economies were trying to do everything else, to the banks, whatever, to keep the world under control. So this split, I think, is back again these days, but under different conditions. And we should, like you say, we should review, reconsider in the training and education, etc., like in this situation.
Yes, I agree. Thank you for the comments and thought-provoking questions. I think we are reaching to the end of this Q&A session. With that, we would like to conclude the event, and thank you to all our speakers for your thoughtful talk. And thank you all for joining me this afternoon. And also, I would like to thank our donors for TISET and our staff members over there behind the scene to make this event happen. And well, there are many ways to get involved with TISET. Please connect with us online. There's barcode to disseminate our information. And after that, I would like to invite you to join us for a little cocktail. You can continue to communicate with our panelists for some more in-depth discussion. And with that, I would like to thank you once more and have a good night. Thank you very much.